given by this particular formula, which is given by QB by 2 pi m, where Q is the charge of the particle, B is the magnitude of the intensity of the magnetic field, divided by, and this mass, m is the mass of the particle. So you can see from this expression, however, that the frequency of the cyclotron radiation does not depend on the velocity of the particle, but rather it depends only on the strength of the magnetic field. So if you apply a very strong magnetic field, the frequency of cyclotron radiation will be higher. But if the magnetic field is weaker, then the frequency of cyclotron radiation will be less. So okay, so now the question is that can we observe this cyclotron radiation from these galaxies? So the thing is that the magnetic fields that is present in galaxies are around 1 to 10 microgauss in strength. For comparison, the magnetic field on the surface of Earth is around 1 gauss. So it's a very weak magnetic field, and the thing is that because of that, any cyclotron radiation that is emitted from these galaxies will have a very low frequency, around 3 to 30 hertz. So this makes it impossible for us to detect cyclotron radiation from galaxies, okay, because of noises and all. So any observation is of cyclotron radiation will not be very reliable for us. So next we look into synchrotron radiation. So universe has a lot of high energy particles, okay. So these may be released in supernova explosions, or it can also be produced in astrophysical jets, okay. So these high energy electrons, when they pass through a magnetic field, they accelerate and they radiate synchrotron radiation. So what is what differentiates between synchrotron radiation and cyclotron radiation is that because they are moving very close to the velocity of light, we have to consider the effects of relativity as well. So we have to so basically you can see that our frequency, first of all, the main difference between cyclotron and synchrotron radiation is that the frequency is different. Now the frequency is multiplied by this Lorentz factor, the square of the Lorentz factor, okay. So Lorentz factor, okay, so basically Lorentz factor is it visible? Okay. So Lorentz factor is basically okay, so basically it's given by this particular expression. So here v is the velocity of the particle, c is the velocity of light. So this is what Lorentz factor is, and you can see that as v approaches the velocity of light, your Lorentz factor also approaches infinity, okay. And when velocity of the particle is not comparable to the velocity of light, then Lorentz factor is approximately 1. So basically you can consider, so basically if the particle is moving at very low velocities, the gamma basically is approximately 1, and that gives us back the cyclotron radiation. Yes.
Exactly, this radiation is the fractional radiation that particles emit the accelerates, or is it a different type of radiation?
Basically, this is when the in this case, the particles are not changing the speed, okay. The magnitude of the speed is not changing, but they are rather changing their direction of motion. So magnetic field, basically, as we see, they just change their direction of motion. So because the force exerted by the magnetic field is always perpendicular to the direction of velocity, so the amount of work done by the magnetic field is basically 0. So the radiation it's emitting is not by this Planck's radiation, but rather it's due to this is something else. Okay. So another thing is that this synchrotron radiation is mostly linearly polarized. Okay. So it is mostly linearly polarized, and the good thing is that the polarization vector of this synchrotron radiation is perpendicular to the orientation of the magnetic field. So if we can map, let's say we have a galaxy and we can know the polarization, the orientation of polarization in different parts of the galaxy, we can just rotate the polarization vectors by 90 degrees, and we can get the orientation of the magnetic field in the different parts of the galaxy. So the question is, how do we determine the polarization of light that reaches from the galaxies? Okay. that is the question. So to do that, the radio telescopes. So we start with the Stokes parameters. So radio telescopes collect data as Stokes I, Q, U, and V maps. Okay, so these are different formats basically. The way these radio telescopes collect and store the data. So the Stokes I parameter is basically the total intensity. So I 0 degree is basically the intensity of light that is aligned, basically intensity of the linearly polarized light that is along 0 degree orientation plus the intensity of light with that is in 90 degree orientation. So we add those two intensities and we get the total intensity I. So that is the Stokes I parameter. So we get Stokes I map using in this particular way. Similarly, Stokes Q map is basically intensity in 0 degrees minus the intensity in 90 degrees. And similarly for Stokes U map, intensity in 45 degree angle minus the intensity in 135 degree angles. Now Stokes V map is dealing with this circularly polarized light. So we will not be using the Stokes V map, but Stokes V map is defined, we obtain it as the intensity of the right-handed circularly polarized light minus the intensity of the left-handed circularly polarized light. And you might have noticed that I have added a plus minus here. So it is because some people use left-handed minus right-handed, whereas others use right-handed minus left-handed. So it really depends on the context, but we are not using the V map, so we will not think about it for now. So the polarization vector, so polarization angle psi can be calculated from the Stokes U and Q map as this particular expression. So psi is equal to half of tan inverse of U by Q. Okay, so this particular formula can be derived. Okay, so one can try deriving this formula for a purely linearly polarized light. One can try to derive this formula, but we'll skip the derivation here. So here's a figure which shows the sign of these Q, U, and V maps. So you can see that when the polarization vector is almost aligned close to the y-axis, okay, so then Q map is almost negative. It is negative, okay. So when basically you can see that Q is I 0 degree minus I 90 degree. So which means that when the x component is smaller, the absolute value of the x component is smaller than the absolute value of the y component, then the Q map is going to be negative. Whereas when the absolute value of the x component of the Q map of the electric field vector is greater than the absolute value of the y component of the electric field, then the Q map is positive. So similarly for U map also, you can see that in this particular region U is positive in these two regions, and for the second and fourth quadrant the U map is negative. So what I've tried doing here is that I tried to artificially create this Stokes Q and U map here. Artificially, that is, I synthetically created this Stokes Q and U map. So I use these two equations, Q equal to minus I times cosine of this expression, and similarly for U map also, to obtain the Stokes Q and U maps. So this is I'm trying to obtain the Stokes Q and U maps using these equations. Originally, however, you will not use an equation to obtain the Stokes Q and U maps, but rather your telescopes will collect this data. However, here I'm not showing you any real data. So we have this synthetic data, and for this synthetic data, I used this particular formula, equation number 5, to obtain the polarization pattern for the light, and that polarization pattern is given by these red vectors in this particular image. Okay, so you can see that. So it follows a nice spiral pattern in these images. So one can obtain this, and by the way, this is not the direction of the magnetic field, but the direction of the polarization of the light. So we have to rotate this by 90 degrees to get the orientation of the magnetic field. So now the question is that, okay, whatever we obtain here, let's say we use real Q and U maps, we obtain the orientation of the polarization angles of the light, but is it really the polarization angle that is originally produced in the galaxy. That is, when this synchrotron radiation is released, okay, from these galaxies, is this radiation affected as it reaches the Earth? Okay, can something influence it? So the thing is that there's something called Faraday rotation. So Faraday rotation is basically a phenomena where when linearly polarized light, okay, when it passes through some magneto-ionic medium. So what is a magneto-ionic medium? Basically, it has ions, okay, and there's a magnetic field present. So that is a magneto-ionic medium, and when light passes through this medium, when linearly polarized light passes through this medium, the polarization angle rotates by some amount. Okay, so it rotates by some amount, and the amount it rotates is proportional to the strength of the magnetic field that is pointing along the direction of propagation of light. So this phenomena is known as Faraday rotation, and as a fun fact, this was also one of the key observations that confirmed that light is an electromagnetic wave. Okay, so it was observed by Michael Faraday, and from where he got the insight that light might be an electromagnetic wave. So okay, so basically this amount of Faraday rotation that you see here is proportional to the square of the wavelength of the light. So if you double the wavelength of light, the amount of Faraday rotation increases by 4 times. Okay, so we add a proportionality constant Rm. So Rm stands for rotation measure. So the amount of rotation so we get equation 6 for the Faraday rotation equation, and so it means that whatever polarization pattern that we obtain here from the Stokes Q and U maps, they may not be the original polarization angle that was at the source of emission. Okay, so by rotating these by 90 degrees, we may not get the actual orientation of the magnetic fields. So what really what really affects this rotation measure Rm? So the Faraday rotation measure Rm depends on the magnetic field along the direction of propagation of light. It also depends on the path length that light travels through the medium and the number density of the charged particles in that medium. Okay, so basically equation 7 is the original expression, but we can approximate it with equation 8. So we can get rid of the integration, and instead of using the we will use instead of using the actual value of the number density of the electrons for different locations along the line of sight, we will rather take the average of the number density of the electrons. As you can see here, we will use the average of the number density of the electrons. So yeah, so since the Faraday rotation depends on the strength of the magnetic field that points along the direction of propagation of light, we can get an estimate of the strength of the magnetic field if we know what is the rotation measure, what is the amount of Faraday rotation that has occurred. Okay, so this is another. Okay, so basically there's a phenomena. Okay, so when polarized light actually can get depolarized, so they can lose their polarization when they travel through space, and this phenomena is known as depolarization, and depolarization can either be wavelength dependent or wavelength independent. So basically depolarization, so we have this beam depolarization, bandwidth depolarization, and Faraday depolarization, out of which Faraday depolarization is the one that is wavelength dependent, whereas the other two are wavelength independent. So to quickly cover through this bandwidth so I'll through beam depolarization. So basically let's say that this is our spiral galaxy, okay, and our telescope actually does not have very point precision to see everything, okay, to point precision. So what we have is we see particular circular region. This is a beam region. So in this region only so there's some limit, okay, so how much accuracy we can see the region. So if the beam area of the telescope, okay, if it's very large, then then we will have a significant amount of beam depolarization. So basically, let's say that polarization angles are somewhat of this sort in these regions, okay. And now, if my beam size is small, I will get, you know, I'll be able to get a polarized light. So I will still observe this linearly polarized light. However, if my beam size is very large, I will find that inside that beam, I have a whole bunch of light, okay, so in different orientations. Oh, sorry. So I have got a whole different orientations of light. So what I will find here, okay, is that I will get unpolarized. I'll find that the light that reaches us, I will not be able to find the polarization. Okay, I will not get basically the polarization angle, because the beam size is too large. So that is beam depolarization. And the next one is the bandwidth depolarization. So bandwidth depolarization, basically our telescopes, they observe the galaxies in different wavelengths, okay. So let's say we are looking at, say, 6 centimeter wavelength, okay. So the thing is that our telescopes measure somewhere around 6 centimeters. So there's an interval, okay, somewhere less than and greater than 6 centimeters. So in this range, the telescope gets the data, and the amount of Faraday rotation that occurs for some wavelength here and over here, okay, can be different. Which means that, let's say that any light that reaches from this wavelength, okay, of this particular let's say this is 5.8 centimeter, and this is 6.2 centimeter, okay. So the polarization. So let's say that after Faraday rotation, this particular wavelength of light is oriented in this orientation, and after Faraday rotation, it is oriented somewhere around this orientation. So because these are two different wavelengths, the amount of Faraday rotation also has to be different, because Faraday rotation depends on the square of the wavelength. So because and if the difference between these two is very large, then we may not be able to find the polarization. Okay, so that is the bandwidth depolarization. And lastly, we have this Faraday depolarization. Now this one is actually dependent on the wavelength. And okay, so to give an illustration of that, let's say that our light, let's say that is emitted from these two regions, okay? Basically, in this region, light, our synchrotron radiation is released from this region. And so synchrotron radiation is emitted from this distance also, and from this distance also synchrotron radiation is emitted from all these distances. So the amount of Faraday rotation that occurs for this light will be more as compared to the amount of Faraday rotation that occurs for any source that emits for radiation that comes from this source, right? Because the distance that this light travels, the distance that is covered by this particular radiation is much more than the distance that is covered by this radiation. So this also can cause differences in the polarization angles, and we may get overall unpolarized light as well. So this is known as Faraday depolarization, and it depends on the wavelength. If the wavelengths are very, very small, then this is almost negligible. However, for larger wavelengths, we have to consider Faraday depolarization as well. So because of this depolarization, we have to add something called a depolarization coefficient. So our original expression for Faraday rotation measure, you see that it was basically the 0.81 times this expression. But now we add this constant called chi lambda. So chi lambda is our depolarization coefficient, and it varies from 0 to 1. So if chi lambda is equal to 1, then there is no depolarization, and if xi lambda is approximately 0, then there is a lot of depolarization, and our light may be completely depolarized. Okay. So the basic pattern that is followed by astronomers to find the structure of the magnetic field is that they first have the radio telescopes, from which they obtain the Stokes radio maps. From these Stokes radio maps, they obtain the polarization pattern, from which they do this Faraday rotation correction. They do this Faraday rotation correction, and then they use the magnetic field model to determine the field parameters. So they determine the structure of the magnetic field in the galaxies. So this is the general procedure in which they determine the structure of the magnetic fields. Okay, so now we start with the model. So how do we model the magnetic field, okay, in a galaxies? So the magnetic field is a vector quantity. So it has it can be written as three components as Br, B theta, and Bz. So these are a cylindrical coordinate system. Okay, Br is basically pointing away. So it's like similar to the polar coordinate system, but instead of just r and theta, we also add a z-axis to it. So that gives us the cylindrical coordinate system. So yeah, so Br, B theta, and Bz are the three components of the magnetic field. So we write it in that way, and we define the pitch angle of the magnetic field as the tan inverse of Br by B theta. Okay, and we define this B. B is basically the strength of the magnetic field that is in the plane. So B is the square root of Br squared plus B theta squared. Okay, so okay. So astronomers have so they have actually made classification. So magnetic fields in galaxies are actually a composition of various magnetic modes. Okay, so when the pitch angle and the strength of the magnetic field are the same, then it is known as axisymmetric field. So you can see in this diagram, so that the pitch angle is the same. So with respect to the Br and B theta component. So wait, I'll just describe the pitch angle geometrically before I go on with that. So okay, so let's say that this is our galaxy, and let's say that at this point the magnetic field is in this direction. So the Br component is going to be in this direction, and the B theta component is in this direction. So this particular angle is going to be the pitch angle. So pitch angle is basically the angle that the magnetic field makes with the tangent to that disk of the galaxy. Okay. So as you can see here, the pitch angle is constant in this axisymmetric field. So you can see that the magnetic field is making the constant angle with this tangent line. Okay, and the pitch angle which we have chosen here is 25 degrees for this one, and the strength of the magnetic field in each of these points are the same. So this is the axisymmetric spiral field, and then we have this bisymmetric field. This is for mode n equal to 1. Okay, so in mode 1, here also the pitch angle is constant, but the strength of the magnetic field is changing as a function of it's changing as a trigonometric function. Okay, so the strength of the field is multiplied by cosine that function. So in this part of so basically in the right side of this galaxy, you see that the field is going in the anti-clockwise direction. However, in the left side, it's going in the clockwise direction. So the magnetic field has flipped its direction. In the half of the time, it's pointing in one direction. In the other half, it has flipped its direction. So that is how the axisymmetric and the bisymmetric fields are different. Similarly, for higher modes, we can also have higher modes also. So m equal to 2 also we can have, and others. So basically the magnetic field in these galaxies are basically a composition of these various magnetic modes. So you have axisymmetric mode and a bisymmetric mode. So let's say there's a galaxy. So in some galaxies, the magnetic field is basically a composition of these two, whereas in other galaxies it's simply just axisymmetric. Whereas in some cases there may be only bisymmetric also, or maybe some higher modes also. So it really depends on the galaxy, and yeah. So that's basically how astronomers are classifying and simplifying their analysis. So now, if we know the pitch angle of the magnetic field, okay. So if we know the pitch angle of the magnetic field, then we can know the intrinsic polarization pattern. So what is intrinsic polarization pattern? It is basically the polarization angle that was at the source of emission. Okay. So it is not the one that we observe here, but it was before Faraday rotation or any depolarization occurs. So whatever polarization pattern was there at the source of emission, that is the intrinsic polarization pattern. So if we know the pitch angle of the magnetic field, then we can know the intrinsic polarization pattern of the magnetic field. So using this particular expression, and this expression basically has a few variables, like you can see that it depends on the pitch angle V, and it also depends on, there's a parameter called the galaxy inclination angle I. So what is this galaxy inclination angle? So basically a spiral galaxy, okay, so it's like a disk, okay. So the disk can be, okay, let's say when you look up out into the sky, or let's say, okay, I'll show you, show it here. I think so let's say this is our telescope, okay. This is our telescope, and this is our line of sight. So our spiral galaxy can be in any random orientation, and the thing is that it may not be completely perpendicular to this line, or it may not be completely flat also. It can be at some angle. So this angle, basically we draw perpendicular to the galactic disk, and this angle is our galaxy inclination angle I. Okay, so it depends on the galaxy inclination angle, our pitch angle P, and theta is basically the position we are taking in the galaxy. So that is how we can determine. So if we know, let's say we know the magnetic field structure of the galaxy, then we can know the intrinsic polarization pattern for that galaxy. Okay. So similarly, if we know the structure of the magnetic field in the galaxy, we can also determine the rotation measure of the value of the rotation measure in different parts of the galaxy. Okay. So because rotation measure is dependent on the strength of the field that is pointing towards us or away from us, so we can also know what will be the rotation measure if we know the magnetic field. So now we will see how the magnetic field, suppose structure is determined for this galaxy. So first step which we usually do is we make a guess of the magnetic field parameters. Okay, so the magnetic field parameters are the pitch angle P and all those. So we make a guess. Okay, so maybe this might be the structure of the magnetic field. So we make a guess, and then we obtain the value of this intrinsic polarization angle and the rotation measure Rm. So out of this we get these two parameters, and from that we can calculate the polarization angle that we should observe. So if our guess magnetic field is, so suppose this is we guess that, okay, this is the magnetic field structure of the galaxy, then this is what we should observe as the polarization pattern. Okay, so for a given, so we guess for a magnetic field, and then we find what should we observe, and this is basically the expected polarization angle for the guess magnetic field. Okay, so the thing is that whatever expected polarization angle we get may not be the actual observed polarization angle that we find from our Stokes Q and U maps. Okay, so our goal is to get a magnetic field, okay, parameters of the magnetic field, such that our expected polarization angle matches with the observed polarization angle. So to do that, basically we define a loss function and we define it in this particular way. Okay, so the loss function is basically dependent on the magnetic field. So the magnetic field that we think, okay, is correct. So this is the guess value, and that is equal to this particular expression. So xi n is, so basically you have n data points. Let's say your data has n data points, capital N data points. So this is basically, we take the summation of this expression, where xi n is basically the observed polarization angle, the actual polarization angle. Sigma n is the error in that polarization angle, and this function you see m, this is basically the expected value of the polarization angle that we obtain for using this equation for tin. Okay, so this is the expected. Yes.
What is this psi n represent?
Yes. So psi n is basically our polarization pattern that we observe. Basically, you see. So basically, when you use Stokes Q and U map, we obtain a polarization pattern. So we get some polarization vectors. So these are basically what psi n is. So we get a finite number of data points. Okay, finite number of. So let's say that at this location we get our psi n. Suppose at this location we get psi n, and so we get for a finite number of points we get psi n. So capital N number of points we get our psi n.
It means it is an experimental value.
Yes, this is the experimental value. Okay, so that is the experimental value. So the experimental value of psi n minus the expected value of psi n. Basically, the expected value is determined using this function. So the model equation of our magnetic field. So we find this expression and divided by the sigma n, where sigma n is basically the error in our observation. The experimental value has some error, so that error is this sigma n, and we find this, we evaluate this, and this gives us our loss function. Okay, so what we are going to do is basically we will try to change our model parameters, the parameters of the magnetic field, such that the loss function, the value of the loss decreases. Okay, so we want to minimize our loss. So, and we do that until until we get the minimum value of the loss we can get. And this algorithm is basically known as gradient descent, and it is also used in some. It is a very common machine learning algorithm. So this can be used here to determine the structure of the magnetic field. So here's a more graphical representation of gradient descent. So basically what you see here is that the z-axis here represents the value of the loss function, and the x and y-axis are the values of the parameter. So let's say that one of the x-axis represents the, let's say, the pitch angle, and y-axis, let's say, represents the strength of the magnetic field. So if that is the case, then we find that we first randomly choose a guess value. So the guess value is given by starts at this red region. Okay, and we want to minimize our loss. So our gradient descent moves through this curved surface and reaches the minima. So the minima of this particular function. So, and that is basically how we determine the structure of the magnetic fields. Thank you. So these are the references for anyone who is interested to go in depth. Okay.
Any questions? Anybody have a question? One question.
Yes.
The field diagrams that you showed of asymmetric and bisymmetric
Yes.
fields.
Yeah.
The view of the galaxy from sideways or top view?
Oh, this is actually face on, directly from the top.
Okay.
So this is the disk, and so we are looking directly.
Okay. So the bisymmetric is that the galactic